Okay, so I'm going to go over the notes for section 1.2. This is short. Some of this should be familiar. So first, we'll just start with the graphs of some well-known functions that we mentioned last time in the notes for lecture section 1.1. Okay, so you have to know the general shape of the graph, but if you to graph it, what you do is you just find a few ordered pairs. And so like for y equal x squared, we know that's a parabola, right? A parabola is it's a polynomial, leading degree is 2. Find a few ordered pairs and just draw the, the general shape of, the shape is a parabola, so just draw a curve through it. And then for the absolute value function, yeah, once again, we know it's V-shaped. Again, just find a few ordered pairs and just draw the curve through it. We definitely want to know the graph for, definitely want to review the trig functions. You want to know the graph of sine and cosine. So once again, just review the graphs of all these functions right here, like y equal 1 over x is a hyperbola. Where is it? Yeah, so there you see number 8 is a hyperbola. You definitely want to know the graph of y equal x, y equal e to the x, sorry. Okay, but here's something you may not have seen, or I think we did teach this in algebra. I haven't taught algebra in a long time. So some functions, the formula is different depending on what the independent variable is. So here you have this function 2x plus 1, for x greater than 1. F of x is 4 for x equal to 1. And for x less than 1, the formula is x squared. And so actually to draw the graph, you would have to, if you're drawing with pencil and paper, you'd have to take your pencil off the paper because it's not continuous. So at x equal to 1, it jumps up to 4. So if you're approaching x from the left, if you're approaching x equal 1 from the left, you'd be going to the point 1 comma 1. But then when you get to 1, you jump all the way up to 4. If you're approaching x equal 1 from the right, you'd be approaching the ordered pair 1 comma 3, because 2 times 1 plus 1 is 3. So you get that kind of funny looking graph or unusual looking graph. Well, we know that domain is the set of all real numbers. Now, what's the range? You actually have to look closely at it. It's not obvious. Like 2x plus 1, if the domain was all real numbers, then the range would be all real numbers, but we're restricted to x greater than 1. So we know that the graph is, we know that 2x plus 1 is positive for x greater than 1. Well, 4 is definitely positive, and x squared is always positive except at x equal to 0. And 0 is and x squared is actually defined for x equal to 0. So we know that the range is 0 to infinity, including the point 0, because when x is 0, y is 0. And then to evaluate f at these certain points, you just make sure you're choosing the right formula. So f of 3, well, 3 is greater than 1, so use the formula 2x plus 1, you get 7. F of 3, 3 is greater than 1, so use the formula 2 times x plus 1, you get 2 times 3 plus 1 is 7. Well, f of negative 2, negative 2 is less than 1, so use the formula x squared, and f of 1 is 4. Okay, so, and then something that you may have remembered to learn at one time from your algebra course, that absolute value is really a piecewise function, right? Because the graph, all of a sudden it changes, as you're approaching from 0 comma 0 from the left, you get this downward, it's a downward sloping line. And then you pass, then as you go past x equals 0, go towards the right, all of a sudden becomes an upward sloping line. You get this V shape. So f of x equals the absolute value of x. So it's just equal to x for x greater than or equal to 0, and minus x for x less than 0. That's basically the definition of the absolute value function. The definition of the absolute value of x is that it's x for x greater than or equal to 0, and minus x for x less than 0. So now let's say we have this function, absolute value of 2x minus 3. Well, when is the input equal to, when do we get 0? What independent value will give us y equal to 0? So solve 2x minus 3 is 0, where x is 3 halves. So the transition point is at x equal to 3 halves. And so for x greater than 3 halves, the absolute value of 2x minus 3 is just 2x minus 3. For x less than negative 3 halves, and that's where 2x minus 3 would be negative, we use the formula minus the quantity 2x minus 3. So this one might be a little bit more interesting. It's this area function, but notice that, so from 0 to 2, the area is increasing. We get this triangle, right? So, and the slope of that line is y equal, the formula for the line is y equal to 3x. And so from 0 to 2, the base would be equal to x. The height would be equal to 3x. And so we know the area of a triangle is 1/2 x times 3x. So for x from 0 to 2, we know that the area function is 1/2 x times 3x, or 3/2 x squared. Okay, now when x is actually equal to 2, that's when it starts, the graph doesn't stop sloping upward, and it's just kind of a flat line. So for x greater than 2, it's the graph is just a flat line. And at that point, so for x equal to 2, 3 times 2 is 6, so the height is 6. So for x greater than, so at x equal to 2, the area of that triangle is 6. So you have to add on the area of the triangle. So that's where you're seeing that for x greater than 2, it's 6 plus. So the 6 represents the area of the triangle. Okay, now you have this area of a rectangle. Okay, so the base of the rectangle, let's say you go out a distance x. Okay, you have to subtract off 2. So you have to subtract off 2. So the base is x minus 2, and the height is 6. Okay, so for x greater than 2, you add, it's the area of the triangle, which is 6. And then the area of the rectangle, the height is 6, and the base is x minus 2. So yeah, we're almost done. This is a short section. Yeah, I think, let's say the graph of one function. How can you use it to get the graph of another, like a similar function? And that's when we have transformation. So let's say the graph of f of x. Now, what's the graph of x of x plus a? So you shift the graph a units to the left. And so minus f of x, you just kind of basically, it's just the mirror image about the y-axis. And for f of x plus 3, you just kind of drag the graph up c units. So look at that example right there. Minus x plus 2 minus 1. So the first thing that we're doing is we're adding on 2 to x. So that means we shift the graph. So originally you have the original, so you take the graph of the square root of x, which you see in that drawing right there, the one that's labeled f of x. Okay, so what are we going to do? We're going to shift it 2 units to the left, because the first thing you're doing to x is you're adding 2. So we have to shift the graph 2 units to the left. Then we're multiplying that whole quantity by minus 1, or by, minus 1. So which means basically it's the mirror image about the x-axis. You're just flipping the graph over, and then you're subtracting 1, which means you just shift the graph down 1 unit. So if you know the graph of the square root of x, you can kind of roughly get by hand, get the graph of minus x plus 2 minus 1 just by using these 3 rules. We're shifting to the left or to the right. If you multiply by minus sign, you're basically flipping the graph over, and then we're shifting the graph up or down, depending on what constant we're adding to the graph or to the function. Okay, so here's one, like an example 15. So you just have a graph of, so it looks like it's a graph of the absolute value of something, graph 15. So how do you get the graph of x minus 1 plus 2? You take the graph that you see in 15. That's the one that's kind of in the black pen. Now what we have to do is f of x minus 1, which means we shift to the right one, and then we lift the graph up 2 units. So the transform graph is in red. And for minus 2f of x, well, we have to flip the graph over, and then we have to stretch it 2 units. And I'm going to kind of skip the example C and D. Those are kind of unusual transformations. So again, if you have any, this is really quick. There's not a lot to say here. So if you have any questions, don't hesitate to contact me.